Hi, welcome to this tutorial on geospatial data analysis in Julia with Rasters.jl. Julia is a high-performance programming language which is a potential solution for the performance bottlenecks that we face with raster data. So either the data is very large and it doesn't fit in memory, or it takes too long to process, or there are many small files because the data is collected every single day, and in many cases that has been happening for years. So what happens is that the size of the data is very large, or it takes a lot of processing to do anything useful, and that's why Julia might come to our rescue. Now, Rasters.jl is a new package in Julia. It's being actively maintained and developed. This package provides basic utilities for raster analysis, and I find this very useful compared to all the other packages in other languages. In Julia, there are several other alternatives, but still, I've worked with many of those over the past 2-3 years, and I think Rasters.jl is by far the best. In this tutorial, we'll primarily use the harmonized nighttime lights data. So nighttime lights is considered to be a proxy for economic activity. And this harmonized nighttime lights data is essentially the combination of two data sets. So there was one data set from 1992 to 2013 and one from 2012 to the current period. And this data set has merged the two. So now you have a long series from 92 to 2020. And in the future, they'll release for subsequent years as well. This data is useful from one perspective, of course, that it provides a very long time series, and that might be useful for studying economic development. But at the same time, the file sizes are very small. So I want you to go ahead, click on the link and download any one file. Now, in case you just want to use this tutorial and not go into the data sets too much, then you can just clone this repository. So either clone from here, or you can download a zip file, and then you'll get access to all the data that we're going to use in this session. The Jupyter notebook, while we are at the repository, the Jupyter notebook is also there. So this rasters.ipnb is the notebook that I'm going to be using for this session. You can view this in Deep Note, just as I've been doing it here. Now, the tools to analyze raster data are very general, especially with single band images like nighttime lights. I won't go too much into bands in this session. I think there are other people covering that a lot better than me. So just consider it's a single band image, which means one pixel at a given time has one value, right? So that's the amount of light in the case of nighttime lights. But yeah, coming back, the tools are very general. So I'm also going to show with some other data sets like aerosol optical depth, which is a proxy for air quality, and normalized vegetation index, which is a proxy for greenery. So it kind of measures the amount of chlorophyll. In addition to these satellite data sets, we also need a vector data set, which is the country level shapefile. You can, instead of the country level shapefile, you can choose any other shapefile that you want, right? Any other kind of polygon. So maybe it could be inside a country, states of a country, or counties of the United States. And you can just replace those. So what I've done is I've just searched for country level shapefile, and I've found something. And generally that's the process. You would just search on Google about the shapefile that you want, and many times that would be available for free. All right. Now, before starting with Julia, I also want to show QGIS because it's a useful tool for visualization, right? So the raster data is like a matrix, and it's a 2D matrix with just values, and it's kind of hard to make sense of things sometimes. So that's why a graphics tool like QGIS might be useful. What I'll do is I'll go to the data directory. So sorry for this. So what I'll do is I'll go to the data directory, go to the harmonized nighttime lights file. This is the same data directory that is there. So in here you see this file, harmonized DN nighttime lights for 2020. You can of course pick another year, but I'm just going to go here and open this image with QGIS. What you can also do is open QGIS separately and then drag and drop the file over there. Now very soon you'll see QGIS opens up and you see the nighttime lights data. Now let's see some urban centers of the world. I think this is Shanghai. Similarly, I think this is somewhere here is Milan. This whole region is very prosperous. And I think this is Moscow. So the idea of nighttime lights is that brighter areas are more prosperous, or as a place gets prosperous, it also gets brighter. So you can either look at time series or cross sections, or you can even look at both. All right, so that's the intuition behind nighttime lights, and this is how it looks, and it kind of looks like what you would imagine night lights to be around the world. Now QGIS allows us to do some other things like overlaying OpenStreetMaps. So just go here in the browser and then you see XYZ tiles and there would be OpenStreetMaps. So just click on that and then it puts an OpenStreetMaps layer on top of this. What you can do is go to opacity and reduce the opacity. So now you can see both of them. So let's see. Right, let me go to a familiar place like Sydney. So you see wherever the boundary of Sydney is, nighttime lights is significantly higher, right? And this is kind of intuitive and it also confirms our hypothesis. Now let's see some other data sets. So as I said, I'll be also showing vegetation index. So I'm going to drag and drop this vegetation index diff file on QGIS. And here you see the vegetation index. So let me just zoom out, and that's Australia. Let me zoom in once again. I'm going to reduce the opacity a bit. And once again, you see wherever nighttime lights is higher and wherever you have more urbanization, according to OpenStreetMaps also, you see that the greenery is less, and that kind of confirms between there is a relationship between OpenStreetMaps, greenery, and the vegetation index as seen from the satellite data. Now, one final thing I want to do is overlay a shape file on top of this. So let me first remove this one, remove this layer of, and I'm also going to remove the OSM layer because it might take too much of my memory. And let me now drag and drop the shape file. So once again, I just drag and drop the shape file, and you see the countries are painted on top of the nighttime lights. So this is extremely useful. That a tool like QGIS is there, and many times it's just that you can't visualize things very easily in a programming language, and that's why you need these tools. However, they are very limited, so the kind of things that you can do are very limited. With QGIS, you can't do many statistical processes. Many things would take very long. However, right now let's look at the intersection between the shapefile and nighttime lights. So I can go here, and in the labels I can put single labels, and that will show me the name of the country. And as you would expect, there's North and South Korea. Let me reduce the opacity. Sorry, I reduced the opacity of the labels. Let me reduce this opacity. And you can clearly see the divide between the North and the South. All right, so in summary, we have raster data, which is nighttime lights in this case, and we have some vector data, that is the world country level shapefile in this case. Now, many times we need to overlay these on top of another, and that's what we are going to do later on in Julia using rasters. Many times you want to look at the total amount of light in a country. So in this case, what's the total amount of light in South Korea? And that's how you can compare to. You can compare the total amount of light in North Korea versus South Korea, right? And you can also compare the mean, so what's the average amount of light. The average might be more useful in the case of greenery. So what's the average amount of greenery in South Korea compared to North Korea, right? So you need the polygons to be able to tell where the raster intersects with it. And that's what we are going to do in this tutorial using Julia. Now let's come back to Julia. Here is the Jupyter notebook that we'll be studying, and I won't be executing the code. Well, it's not a problem, but it's still a bit nicer if it's already executed. So I'm just going to look at this deep note viewer of the Jupyter notebook, right? So the first step is to use certain packages. So like in Python, you have import and then a library. In R, you have a library and then the name of the library. In Julia, it is using. So you say using rasters. And in this case, you need a version of rasters above 0.4.6. Then you have plots, because we'll be plotting things. And from statistics, I think we need mean. Then to open shapefiles, we need shapefiles. We'll be doing some data frame manipulations, and for that we need the data frames package. And there'll be one place at the end where we'll be using dates, because we'll be combining images over time. So we need the dates library. So the first step is to use a raster function to load a raster file. And in this case, we load the harmonized nighttime lights file. So we just provide the path of it, and then we store it in a variable. And in this case, we call it raster. You can call it ing, you can call it nighttime lights, just any other name. Here it loads the file, so it tells from where to where your raster data is. It says from minus 180 degrees to plus 180 degrees. And it has, so this is longitude, and it has 4201 columns. Similarly, it says on the y-axis, it ranges from minus 65 degrees south to 75 degrees north, and it has 16,801 rows. And here you see the value, so it's like a 2D matrix. As I said, one more thing. As I said before, band is always 1. So these values look very odd. So all of them are 0x00. So the top left is 0 and the bottom right is 0. So in between you have values, but it just doesn't show you all of them. So it looks like all of them are 0x00. But I assure you there are some values in between. Okay. So we can just use the plot function to plot our raster file, and then you get a beautiful plot of the nighttime light state of the world. So let's go to indexing. So we can index with the row and column numbers, but we also need to put the band, and in this case it's always 1. So we have raster 10, 10, 1, which means 10th column, 10th row, and the first band. So in this case the value is 0. So this is just 0 written in hexadecimal. Similarly, you can have rasters 1000th column, 1000th row, and the first band. And with this pipe operation and the int function, you can convert it into an integer. So in this case, again, it is 0. Now let's use the longitude and latitude for indexing. So you say raster, and then in the square bracket you say x near, and then your longitude, and y of near your latitude, and again band equal to 1. So that gives you a value, and we can convert that to an integer just as we had done earlier with just a pipe and an int. So this time it's 63, and this is the maximum value of the harmonized nighttime lights. Now let's go to shapefiles. So we can load a shapefile using the shapefile.table function from shapefiles. We just put the path of the shapefile, and then we can make it into a data frame. Now this is not necessary, but it just makes some manipulations a bit easier. In the next function, in the next expression, we remove the missing data from the shapefile. So this drop missing is from data frames, and it removes the rows with any missing data. So we have basically, earlier we had 193 countries, now we have 192. So one country we had some missing data. Alright, we can visualize the shapefile. So just plot shp.geometry, and then it shows you the shapes. let's select a particular country. So let's say you select Japan from, so you say in shape name, you can select where shape name is equal to Japan, and that gives you the number, the element number. Okay, so I want you to change it to something else, maybe Bolivia, Vietnam, Argentina, India, something else. Okay, and then you can plot the geometry of Japan, right? So there you go. So just plot shp.geometry and then this. Now I come to cropping. This is very important because normally we don't use the entire world data. We crop it to the region of our interest. So there are two ways of cropping. We can crop using shapes. So we can just say crop and then a raster, and then we say to, and then we put the shape. So shape shp.geometry and then Japan. So remember, this was the Japan shape as we saw earlier, and we can just crop with this. So we get a new raster file that is cropped to this polygon. So you see it here. We can just plot that, and you see Japan. All right. But you can also crop using bounds. So you can put the latitude, longitude extent, or rather the longitude, latitude extent like this, and then you can just say raster of bounds, and then you need to put these three dots, and then you can plot. So you get this. So in this case, I've taken the bounding box around India. You can choose whatever you like. The next concept is masking. Actually, we don't need this comment, so just please ignore this. Masking will remove all the points outside a given polygon. So in this case, we choose the Japan polygon once again, and we can mask with it. So anything that is outside the polygon is marked missing, and this is very clear with the plot. So you see this very nice plot of just Japan. So in the previous plot where we had cropped, you could see some parts of China and South Korea and North Korea. But in this part, it is just Japan, and all the sea outside is just considered missing. Now, once we have the masked image, we can do summary statistics like mean, sum, and so on. So we can say sum, and then we say skip missing, so don't consider the missing values. And then you can do a sum of the values of Japan. We convert that to int, and then we print. So this is the sum of light of Japan. Then we can do the mean. So we just change the sum to a mean. And in this case, we want a floating point because the mean might not be an integer, right? So the mean, the average amount of light is 11.36. Similarly, you can do median. And these mean and median functions are from the statistics package. The sum is in base Julia. So you see the mean amount of light. Now suppose we want to do it for every country. So suppose we want to compute this summary statistic for every single country. So suppose we want the total amount of light, or the sum of lights for each country, or the mean of light for each country. So that's called zonal statistics. So there's a function called zonal. So you say zonal, and then you put your function. In this case, it's sum. It could be mean. It could be median. Then you put your raster file, and then you put the geometry. Now, I'm not saying geometry of Japan, I'm just giving the geometry. So this gives the geometry of all countries. You can subset it to just get the geometry of a few countries or a set of countries or so on. Right? So this is the sum of lights of each country, and this is an hexadecimal, so we can just convert it to an integer or float. In this one, I converted it into an integer, and then I sort my data frame with the amount of light, right? So I have the biggest values first. So you see the most amount of light, so the total amount of light is highest in the United States, as you would expect, because the GDP is also the largest. And then you have China, right? And once again, it's something that you would expect. The third you see is Russia. Now this is probably to do with the limitations of nighttime lights data, that it's not perfect. Okay, but this is kind of the workflow of nighttime lights research that we do. We download the data, load it, we make some plots, and we do this zonal statistics. finally, we come to a different concept called data cubes. So we can combine images over time to make cubes. So let's look at the data. Sorry. So let's look at the data. So if we see this folder called models AQ, then in this one we have images over time from 2020 January to 2021 December. So we have 2 years of monthly data. What we can do is we can provide the path and then we can read all those files together. So we say path of the directory where all the files are. We put a dates for the dates corresponding to the files. Then we can put bounds. So this is not necessary, but let's say I'm only interested in the air quality of India, then I would take a bounding box around India. Right. This is often useful because the data is very large, and if you don't crop it with the boundary, then it may not fit in your memory. Now I can create a list of files and I can load the rasters one by one. But here is a trick. So you say for I in path file list. So for each file, raster of I, right? So raster loads the file. So load each file, but you put this extra keyword argument called lazy equal to true. And what this does is that it doesn't actually load the data in memory, but it just tells where the file is. And you can crop it. So you don't need to load the file in memory to crop it. All right. So in this case, when you run this line, you're not consuming any additional memory because it's all just out of memory. It's just telling the location of the data and the bound of the data because the data is indexed. So you can do that. And then finally, you can create timestamps and then use these two commands to combine them into a data cube. So here you see, now I get a 345 times 338 times 1 times 24 because there's 2 years of data. Band is 1 and there are 345 columns, 338 rows. So we get a 3D cube. Now it's a 4D cube, but let's ignore, it's a 4D something, but let's avoid the band. All right. So we have X, we have Y, we have band, which is 1, let's ignore that, and we have time. So your time ranges from 1 to 24. Okay, and you get these values. Now we can just plot one of them. So let's say we do view and then data cube, band 1, time 1, and then we plot. So we get the first plot of India. We can change this time to something else and that will correspond to a different month. We can also find the time series of a particular pixel. So let's say we are interested in the time series of this pixel. So this is where I am, this coordinate, and we had earlier also looked at the night lights of this pixel. So in this one, we take the, we use the normal indexing to find the time series of this coordinate. So that's all. I hope you have learned. Just change various things. So just change this bounding box to your favorite country. Where I had selected Japan, just change the bounding box to that. Yeah, in zonal statistics, maybe instead of sum, change it to median, and then just see what happens. Just do some experiments and just try to learn from the notebook. Thank you.